Welcome everybody. My name is Rufal Makuria. I'm with Unified Streaming, and today I will present our contribution, our open source dataset track contribution tools for live CMAF ingest. So just to give a brief outline of the presentation, so I will start with explaining the CMAF ingest workflow. Then I will also motivate a bit why this new CMAF ingest protocol was developed. I will give an update of the status of this new industry specification in the Dash industry forum. So after that, I will jump into the actual contribution of this work, which are tools for sending and receiving a CMAF ingest, and also some CMAF test content and metadata conversion tools. So that's what I will present. So this is a C++ based implementation that we did to support this specification work. Then using that, I will highlight two example use cases for CMAF ingest in distributed streaming workflows, where we think it's beneficial to deploy CMAF ingest. Then I will detail a Docker-based configuration where we deploy the developed tools together to implement some of these use cases. And after that, I will show some of the experimental results that we achieved with that. So what's the CMAF ingest workflow? So CMAF ingest is basically uplink usage of CMAF. So basically we are using from a sender, which could be a file or an encoder. We're using CMAF with HTTP post or put to send content to a CMAF receiver. That could be a storage, an origin server, or a CDN that uses that CMAF content to distribute it using well-known streaming protocol like Dash or HLS downlink. In this case, usually CMAF is combined with HTTP GET. So why is there a need for a new CMAF ingest protocol? So before starting this work, we looked at some of the alternatives. So some alternative include the smooth streaming ingest or RTMP. However, as these are proprietary and not so well maintained, some new features are lacking. So when new codecs or new profiles come out, they typically are not supported by these codecs. And also these protocols are proprietary, so that hampers widespread adoption. Then sometimes Dash or HLS is also used for uplink transmission, so using HTTP post. However, this is also not well specified and it can be complex, as your post URIs will need to match with what's in the manifest. Then MPEG-2TS is another popular format. However, it's gradually being outphased for streaming in the internet. Then two other popular protocols are SRT and ZXI. However, we consider this pre-ABR encoder. So this is more a protocol that you would use prior to your streaming headend start. So CMAF is an ideal output format for ABR encoders, as this format has been designed for adaptive bitrate configurations. However, the CMAF uplink is not yet defined, even though it's a popular and standards-based format supported by Microsoft, Apple, and many of the other companies in the ecosystem. Right, so let's dive right in. So Unified Streaming, we actually led the task force in the Dash industry forum to develop a media ingest specification. So we focused both on a CMAF ingest, so CMAF with HTTP post, as a Dash HLS ingest, which combines Dash HLS with HTTP post. And the main goal was to achieve interop between encoders, packagers, CDNs, and so on. So this is not a client-facing specification. So the specification was approved and published, and many of the companies in the well-known companies have contributed, including Microsoft, Facebook, and BBC R&D. So the specification is available here on the Dash Industry Forum website. We recommend anyone interested to have a look at this. All right. So what about the tools that we developed? So basically, CMAF Ingest is basically a protocol between an ABR encoder and an origin server or a CDN. So the encoder is the source, and the origin server or the CDN is the receiver. So we implemented in C++ the sending of CMAF content. So basically sending of CMAF tracks, including error correction and real-time logic. The tool also includes a functionality for patching the static timestamps of the assets to real-time timestamps and support for TLS encryption and HTTP authentication. And also to support low latency workflows, HTTP chunk transfer is supported, but also fixed length headers, so short requests of each CMAF fragment. This is also supported. So this is for the CMAF sender. On the right side, you see an example script of running the C++ code. Then next, we also developed a simple receiver, which is a Node.js server, which concatenates and stores the received CMAF tracks. Right now, it does not have support for just-in-time packaging, but we also provide a better receiving support using a plugin model for Apache, which is something that unified streaming already provides. So as an example command line, you can run the receiver using a node, as seen on the right. Then one peculiar aspect or a slightly different aspect of the CMAF ingest is the fact that for the metadata, sparse tracks are used. So we observe the metadata mechanism in CMAF is based on dash event message box. However, this is not so good for fast processing or multiplexing, as you need to scan the entire media data to find your metadata. So to address this, we developed a metadata track format that can be used to carry event messages in a similar way as subtitles are stored in ISO-BMFF. So this work is also ongoing in MPEG to be a standardized application format. So we included some tools to basically convert a normal CMAF with dash event message box to a metadata track, or to convert NPD events to a metadata track, so that they can be sent using the ingest sender protocol. All right, so also our contribution also includes some example chunked CMAF content. So we have AVC video with 0.96 second chunks. We have an AAC audio. We have subtitles with WebVTT in 5 languages in fragmented MP4 CMAF, and the time metadata track. So together, if you ingest these tracks together, you cover all of the different features supported in the ingest protocol, which includes subtitle, time metadata, video, audio, ingest. All right. So with these tools, we played a bit with these tools to emulate some of the use cases that we had in mind. So one of them is edge computing. So basically, we run a centralized cloud data center that is the source. It could be an ABR encoder running there or a storage node sitting there. And then we use the CMAF ingest to push using HTTP post to an edge receiver node that resides in the CDN. That is a receiver, and then that receiver can cache a single CMAF format and do some on-the-fly packaging for streaming, and also some content customization and so on. So some advantages that we see in this setup is that we can have a more smooth egress traffic pattern from the centralized cloud to the CDN by using HTTP post and CMAF, single format. And we can deduplicate the cache by only storing the CMAF fragments and generating dash or HLS segments on the fly. And also we can achieve some more content customization at the edge. So we implemented this by having the sender in the centralized cloud, the receiver in the edge cloud, and then we use browsers as clients to emulate the use case. So another use case that we envision is quite similar. But in this case, we target low latency. So for those of you who followed the specifications around HTTP low latency streaming, it's mainly about controlled latency. So basically trying to get a latency of around 3, 4, or 5 seconds. So in this case, we use the CMAF ingest HTTP post in a similar manner. We send from the ABR encoder using an HTTP chunk transfer to an edge receiver, and that edge receiver then can do the latency configuration. So for example, in low latency dash, there is an element called service description where you can signal to a client what the latency should be and so on. And then also we basically also reduce potential request forwarding from the CDN to the centralized cloud in this architecture. So clients will always get their segments as they are available. This can help in having, for example, rate adaptation algorithms function properly, as all segments are served over the same distance. So to implement the setup, we created a demo that deploys the CMAF C++ ingest tools and the Node.js and Origin servers in Docker containers. And then to compare to a legacy CDN, we also implemented an Nginx reverse proxy cache. So in the legacy setup, we deploy both the ingest source and receiver in the centralized cloud and Nginx reverse proxy cache in the edge cloud. While in the edge computing setup, we move the ingest receiver to the edge cloud. And the same for the low latency setup, where it's also possible to configure the service latency at the edge. So in our setups, this is not part of the Docker container setup, we use the Edge browser, Dash and HLS support, and the smooth play ready player to emulate the different receivers. So these are some of the results. So on the left side, you see the cache size after streaming the content. So here you see that in case of a Dash only transmission, CMAF still has some overhead. However, in the case of multiple protocols or multiple DRM or any customization, you can see that the cache size at the edge remains constant, while for a reverse proxy cache, it would increase. Then right above, you see the two runs that we did. So left top is CMAF ingest, and the bottom is a reverse proxy, and the right is also reverse proxy with Dash and HLS. So one thing that you can see is that the egress traffic peak is much higher when using a reverse proxy, and also the variation in egress traffic are much higher. So basically, by using the CMAF ingest between the centralized data center and the edge, we achieve a much lower egress, but also a smoother egress. And then in the last result, we show some of the request response time, both for requesting manifest and M3U8. So in both cases, we achieve request response times under 40 milliseconds, both for the case when the edge multiplex is done, when the cache is already full, or when the cache is cold. So the setup is still achieving a high performance and low latency. All right. So now I'm jumping to my conclusion. So we presented the CMAF ingest, sender, receiver, and metadata track converter and test content. We showed some performance benefit in edge computing and low latency streaming. We mainly want to emphasize this new industry standard or specification that combines HTTP post or put with CMAF. So we mainly target some of the streaming use cases, so large-scale streaming, like ones that is happening in OTT platforms. However, user-generated content might be another use case. So we also added some capabilities beyond what is in FFmpeg. So FFmpeg has similar functionalities today. However, it does not support subtitle, it doesn't have good CMAF support, and also it cannot patch the timestamps very well. So in future work, we would like to do a little bit more on the SCOTI35 metadata insertion. We would also like to consider adding Dash and HLS support. So basically Dash HLS CMAF. And then maybe to consider adding the just-in-time packaging to the receiver, and maybe consider other use cases. So I thank you for my attention. My name is Rufael, and feel free to contact me at unifiedstreaming.com. Thank you. Thanks also to the organizers of this excellent conference. Thank you very much.